So if you want to sign in for some reason, you're free to do so at this QR code. But we're going to skip through this. So for those that may have not attended the workshop, this is an agenda of what we kind of covered up until demo 3. We didn't really get to that part, but I'll be going through each of the demos and the information right now. So we're starting off with basic circuitry, some pretty fundamental knowledge that you'll need when you're interacting with creating circuits, circuit calculations in general, specifically just the relation between voltage, current, and resistance, and some circuit what to not to do's, like just to stay safe, like open circuit, closed circuit, and short circuit, stuff like that. We're gonna do input processing, and output. Doesn't make sense if you read it like that. I'll go in more in depth. Digital versus analog signals, simulating analog with PWM, introduction to GPIO, setting up the remote environment, and parts you're going to be using for the workshop. Now, again, if you guys weren't at the workshop, I will kind of briefly go through these, but I'll be focusing more on the demos. For those who did attend the workshop, you already should know what all of these are. I think everyone got a pretty good understanding during the presentation, but let's begin. So basic circuit knowledge, we have voltage. So it's the electric potential energy that allows for current flow. So if you think about it, a lot of electrical engineering can be like kind of you can kind of use like water to kind of explain it. So let's say you have two lakes. If they're at the same level, then there's no flow of water between them. It's just stagnant. But let's say one was below the other and you had like a connection between them, water would flow from the top to the bottom. So the voltage in this case is that difference, the height difference. So it's allowing for current flow. So imagine the water is the current, and then the resistance would be anything between that path from one lake to the other that's slowing down that water. In this case, it would be like electron flow. So yeah, so current is the charge going through the circuit, and the resistance is, again, anything that limits that charge. So the relationship between those three variables can be summed up pretty easily by this equation. V equals I times R, so voltage equals current times resistance. Depending on what you need to solve for, you can just rearrange these variables and solve for like current and resistance, which is pretty simple. And you won't really be needing that much when it comes to like designing circuits. One reason you might need it is like you're trying to regulate power to a specific circuit element. And that you'll have to calculate what kind of resistor to use, like what value resistor, so that the current isn't too much for the specific device. So in this case, we're going to be using a resistor for an LED because normally the resistance is negligible, meaning that the voltage is set, let's say, to 5 volts. And in order for this equation to remain true, let's say R is very, very, very small, then I, the current going through that device, in this case, the LED, would have to be very, very large. And the LED is not capable of handling that kind of current. So we want to add the resistor to bring the current down. But that's for a little later. In terms of circuit, like terminology, an open circuit is when there's no voltage difference. So let's say I had these two wires, my buddy over here. If they're separate, there is no voltage difference. Right now, they're not connected to anything, but if they were, let's say one was connected to the negative terminal of the battery and the other one, the positive terminal. If they're not connected to each other, then there's no voltage difference. But if I were to connect these two together, and then again, these being connected to a battery, now there's a voltage difference between let's say we're using a 9 volt and 0 volts. So the voltage would be 9 volts in the wire, and you would have current flowing through it. Now, If you were to do that, the only thing that would happen is the wire would heat up because there's again negligible resistance. So you're going to be losing all that energy as heat. But that's another thing. So closed circuit is when again you close the circuit, completing the loop. You create that potential difference, or at least you connect it. And then a short circuit is when you have a closed circuit and it becomes an open circuit, but you didn't mean it to become an open circuit. Now that usually happens again when something, you're giving too much power or too much current to a element that cannot handle it. What will happen is the wiring for that device will get so hot that it'll melt and open that connection. And that doesn't allow, again, that potential difference, so there's no current flowing. What could also happen is it makes contact with another element that's not supposed to receive that kind of current, and it will short that out. So you would just want to be careful with this when you're wiring up stuff to the Raspberry Pi and the I guess this H bridge, making sure, because the terminals on the Raspberry Pi have limits, so you have to make sure you're not applying, let's say 18 volts. Let's say you had 2 9-volts in series. You want to make sure that you're not putting 18 volts into the pins of the Raspberry Pi, otherwise you'll cause a short. And damaging one of these would kill the whole thing, and you're stuck without a Pi. And in today's economy, it's really hard to get your hands on these at a cheap price. Oh, MSRP. But moving on into inputs, processing, and outputs. What I kind of mean by this is everything you're gonna do in internal comp and robotics in general involves one, reading an input from some kind of sensor, or in this case, you'll be using your phone as a controller. So you'll be sending input through your phone. That input comes as either an analog signal or digital signal, depending on what kind of sensor it is. Usually anything interacting with like wavelengths and whatnot is going to be an analog, and like on and off would be digital. So whatever signal that you input, you're going to do some kind of processing. So any logic, checking if this value is greater than that, checking for equivalency, whatnot. And basically you're going to set whatever the output is. So let's say I had a button and I pressed it down. If I'm checking for when it's pressed, I'm going to evaluate that logic and then output what I want to do based on that input. So let's say I wanted to output a 1, for example, as a digital signal, or high. When I press the button, I would be doing that. I'd be checking if it's pressed, and then I would output the signal that I want. This kind of slide is a little messed up because you can take any number of inputs and have any number of outputs. What you're only limited to basically how many pins you have, and how many devices are connected to, I guess, whatever you're making. Oops. So digital versus analog signals. So we interact in electrical engineering with 2 types of signals. It's digital and analog. So digital has characteristics of either being high, which means the max voltage that is outputted by the device, or low, which is ground or zero. Well, not ground, but zero. So with a digital signal, you can only have full power or no power. And it's not continuous. So if you look at this image right here, you'll see that there are gaps between that vary based on, I guess, whatever the input signal is or output signal is. And you'll see this most commonly in computers. That's how, with the use of specific gates and whatnot, that's how you implement digital logic. But that's a whole nother topic. If you're in electrical and taking electrical engineering classes like 118 and whatnot, you'll actually get to learn more about those and actually implement digital logic. but that's another topic for a different time. You don't really need to know that for the purposes of internal comp. And then moving on, we have the analog signal. So an analog signal is different because it has a range of values, and it's not high or low. It's again a range of values. So, for example, when we're doing like PWM output or not, we're simulating an analog signal. So that means that we want to get a voltage between, for example, 0 or 5 volts. That's not 5 or 0 volts. We want to get, let's say, 2.5 because we're not trying to supply full power to the device. We can do that with an analog signal. So usually analog signals can be both positive and negative. But in our case, we're only dealing with positive analog signals. And you'll see that these are continuous. So we can, they're composed of just sine waves. Some of them are just a bunch of sine waves connected. That's a lot of like just 342, Fourier series stuff that you don't need to know. And most of the analog signals that you'll be interacting with are from sensors. For example, if you have a potentiometer, what it's going to do, it's going to have a variable resistance. So if you were to hook it up to like, let's say something like a Raspberry, well, let's say an Arduino, and you connected the signal pin, you'll get a range of values between like 0 and 1023, which would be representing the changing in voltage. Without it being just 0 or 5 or 0 or whatever the max is. So this is going to be pretty useful, especially if you have to control motors, because you don't want to always control them at full power. You want to change the speed or change, let's say, the brightness of an LED, which we'll be doing later. So what is GPIO? So GPIO stands for General Purpose Input and Outputs. That's what you see on literally any like Arduino, Raspberry Pi, literally any, even like well, not your motherboard. That's different because it's not general purpose. They're made for specific applications, but any pins like these that you see on like a Raspberry Pi, where you can program the pins and have them output whatever logic that you want. Yeah. So these can be controlled using software. So if you look at this schematic right, or well, pin out right here, you can see what each pin does. So not all of them are the same. Some of them have different functions because they're connected to different circuitry within the microcontroller, or I guess the Raspberry Pi or whatever computer it is. So you have like 5 volts. This is your power, or VCC as it's most commonly referred to. Then you have your ground. So connecting 5 volts to ground will create that potential difference. Don't do that, but that'll be useful for later. Oops. And then we have a bunch of different GPIO pins that have, so these ones that don't have any other additional text are just digital pins. The other ones are also technically digital pins, but there are several that have PWM functionality, which is what we're going to be using to simulate an analog signal output. So yeah, this gives you a better idea. Where you have GPIO is just the green one, so those are only digital. SPI is a specific communication protocol, I2C and URL same. But then you have these ones here that do PWM or PCM. Which is going to be important later. There should be 4 of them. 1, 2, 3, 4. I thought there was one over here. Never mind. Then 5 volts and 3 volts. But yeah, that's the basic gist of GPIO. Now let's move into pulse width modulation, PWM. So again, like I mentioned, we want sometimes to output a signal that isn't 0 or 5. Now, we can't exactly just output that analog signal because we can't generate that range of voltages. But what we can do is basically simulate it with a digital pin that pulses at a specific frequency and at a specific duty cycle. So what I mean is what you can see in this image here. Let's say we have a signal pulsing for, at let's say 50 hertz. So 50 times in 1 second. So now let's say for each period of that pulse, the signal is only on for a quarter of the time. So if you look at this first, well, I guess the second graph here, you'll see that the signal is on for a quarter of the whole period. And what that does is that it simulates like an average voltage. So the voltage here would be whatever, I think it's 1.25 volts in this case. So the duty cycle refers to how long the signal is on versus how long it's off. So let's say I have 50% duty cycle, the signal is on for 50% of that period and then off for the rest. If I have 75, it's on for 75% of the pulse, and then it's off for the 25% remaining. 0 means it's off the entire time, and 100% means it's on the entire time. So we can change the frequency and change the duty cycle to get that voltage range that we want to simulate to control the speed, or I guess power output of whatever pin that we need. Now, again, this is only some pins are capable of this. On Arduinos, they're like analog outs or A something. For Raspberry Pis, there's PWM pins, and there are only 4 of them. So they're not as common as just digital pins. So what was kind of covered in Audit's workshop with like the bash and Python is how to SSH into a Raspberry Pi. So he should have given the gist of how to do that. So we're not going to cover that too much in depth in this workshop. I will show you that I'm connecting to a Pi, but I won't go too far into it. Now, so this is actually going to be a little different than when you're actually working on in the lab. One way you can, again, connect to the Raspberry Pi via SSH is using PuTTY. So you'll download the PuTTY app, you'll put in the host name or IP address of the Raspberry Pi, and then you'll enter the credentials and whatnot. For the purposes of this workshop, I'm going to do it a little differently. I will also explain alternative methods to connecting to the Raspberry Pi, but I'm going to do it in the way that best fits my needs for now. And then I will, again, post alternative ways of doing it later on. So let's see, it's the next. So I'll get into that a little later. I just want to go briefly through the parts that are available. Well, were available in the workshop. Some of these you won't be using for your internal comp project, but the main ones to really look out for are the breadboard, the Raspberry Pi, the motors here, the servo, and the H-bridge. Those are the main ones that you need to know for the internal comp project or your internal comp robot, as you'll definitely be using all of them, hopefully. Maybe not the servo, depending on what your design is, but we would encourage you to use the servo.
I have a question.
Huh?
What is an H-bridge?
Oh, that's later. Oh, so I guess to kind of answer Summer's question, the H-bridge is a motor controller that we'll be using to regulate the voltage to the motors, which allows us to change the speed of the motors and the direction of the motors. Now, this is much easier to use than trying to do it yourself, or like wiring up something yourself, because most likely you're just going to be doing it in one direction. You could change the speed, but it's a lot easier to use a motor driver to kind of do this for you. And we'll get into how to control it later on in the workshop. But I kind of want to go over what the actual breadboard is. So let me just stop sharing for a sec so that I can focus on, I guess, my camera input for my phone. So this is a breadboard. Camera is not lying in the middle, but so this is a breadboard. Yeah, no, that should be fine. Yeah. So if I'm pinned, what is it recording? All right, this should be fine. I don't know how well you'll be able to see this in the recording, but I think it would work out. Yeah. So looking at this, you can kind of see a few things. So mainly you have on each side, you'll have these two kind of separate rails, and then you'll have this middle section area that's a little different. So going through how these are wired, if you look at these terminals, you'll see that there's a blue line and a red line indicating which ones you should use for VCC or power in, and then ground, which is the blue. So how this is wired is this whole channel, this column is connected. So all these pins here are connected to each other. So let's say, for example, I plugged in 5 volts up here. If I plug in something else down here, I should be able to get the same 5 volts. Or let's say if I sent a signal here, if I plugged in anything along this channel, I'll be able to get that same signal. Same thing for the negative side. So when it comes to like power stuff, what you want to make sure is that you are connecting the positive and negative on the separate columns and not on the same column. So if I'm gonna, let's say this wire is my VCC in, I'm gonna put it in the red channel, and let's say this ground wire over here is connected to my ground on a Raspberry Pi. I'm gonna plug it in there. And I'm not going to plug in the ground, let's say, to the positive. Otherwise, what will happen is current is going to flow where resistance, current is going to flow where with the least, towards the least resistance, or in the, I don't know. So basically, the wires have very, very little resistance, and the channels here also have very little resistance. So where the current's going to go, it's going to pick the path. Oh, there it is, the path of least resistance. So it's going to flow from positive and go back into ground. And again, you don't want to do that because anything else on this channel won't really work. And you might risk shorting the board, the Raspberry Pi. So make sure anything, let's say, is 5 volts is on this channel and ground is on the other channel. Same thing for this side, it's wired up the same way. Now, when it comes to this middle section, you see it's kind of, you have numbers indicating the row. What direction does it pop up? Yeah, let me zoom in on that. So you'll have numbers indicating the rows. And then you got these letters at the top, which don't really do anything. But what's important is to reference the numbers. So the numbers mean that each row is connected to itself. So let's say I start off with row 1. Each of these 5 pins going horizontally is connected. But if I go down to row 2, that's not connected to row 1. So that applies for all of these rows. They're connected horizontally, but not vertically. Now, this channel in the middle kind of acts like a separation. So these rows are not connected with these rows, even though they're the same row. They're separated. This is very useful, especially for like these chips like this, where you have different inputs for each of these pins, and you can't have them connected to each other. So I wouldn't put this in the middle of the board here, on the side of the board here. Otherwise, it would probably break something, since one of the pins is not getting the appropriate signal with the appropriate current or voltage. So again, this side, just like this side, is connected horizontally and not vertically. So just to recap, the side rails are connected vertically, not horizontally, and the middle rails are connected horizontally, not vertically. Sorry, a lot of words. Yeah, so that's the basic of the breadboard. Here you also have your Raspberry Pi with the GPIO. We're going to go into the specific pins you're going to be using a little later. This is a basic motor. It does motor stuff. So all you need to do really is apply. So let's say I connected this really quickly to the Raspberry Pi, which is also plugged in, and I'm using the Raspberry Pi as my power source. I'm going to plug in the VCC and ground to my breadboard over here. And now if I were to plug in the motor to the same channels, you start hearing that the motor is indeed spinning. Let's see if I can. Yeah, that should be pretty visible on video. So yeah. But obviously you don't want to just have it on and off based on when you plug it in. You want to be able to control it with whatever logic is in your program. So we're going to go over that at the end, at the last demo. So yeah, this is a resistor and an LED. So this is the resistor you'll be using for controlling the LED. Again, just making sure that the current in the LED is not too great to the point where it'll damage the LED. LED is a light emitting diode, so current will only flow in one direction. So if you, let's plug this in really quickly. If you know, so there's going to be a longer lead to the LED. You want to make sure that's going to the positive side and the shorter one to the negative. So if I plug this in, you'll see it light up. Again, full power is going to the LED because this is just 5 volts being applied to it. There's no, it's not, you can't even turn this on and off. These are always going to be on 5 volts and always ground. But let's say if I were to reverse the direction of the LED, nothing happens because it's a diode, so current only flows in one direction. And then this is the servo motor. So you'll see you have kind of 3 cables. You're gonna have power, ground, and then the signal wire where you'll input a post signal to control the rotation of the servo. I'll actually get a blue one with the what's it called? The little fin attachment thing, just so that I can show rotation a little better. I'll get the tip. All right. Give me 1 second. I just need to get something. Let's see.
Wait, hold on. Did you not join audio?
Huh?
Did you not join audio?
Oh no, because it's gonna play audio on my computer.
Oh, okay.
Oh, so my phone. Yeah, I'm running a really weird setup. It took me like an hour to set up, so that was a good use of my time. But I had my phone kind of connected to my computer, also on the call, but I had to make sure to mute it, otherwise you'll be hearing an echo. So yeah, this is a different servo. They're really similar. It just, I think this attachment works for this blue one and maybe not the other one. So I want to use this also. Brown is ground, red is power VCC, and orange is signal. So same thing, and you just got to apply a specific pulse signal to control the rotation. So now let me just share the workshop one more time. All right, I'm in the slides. So now it's demo time. So let's kind of go into the schematics and wiring that we have to do. So I'm actually glad I can kind of record this because I think you guys should be able to see it and understand it better. I know that during the physical workshop, it was kind of hard to see which pins I was using because everyone was seated away from the projected screen and things were blurred and whatnot, but that's whatever. So what you commonly see when you're designing circuits is not this one here on the left, but this one here on the right. Wait, it's going to be whatever board or chip or whatnot that you're using. And the pins are going to be labeled depending on what they do. And you're going to have like a very basic illustration for each component so this zigzag of wires here is the resistor. You can see R2, resistor 2, or I don't know why it says 2 because it's the only resistor, but whatever. And it has this one's rated for 225 ohms, which is exactly the one that I have here. I might do some other workshop going over some other parts. And then the LED, which has the image of a diode, which is everything like this triangle and then the line, and then these two lights these two arrows indicating that it's an LED, so light emitting diode. And then these values down here, I think, are the power ratings or current. I'm not sure which one, but yeah. So this is what you'll most likely see when you're doing schematics, and a lot of programs use this kind of way to format schematics. But for the purposes of just making it more beginner friendly, and I guess visually appealing, I wanted to show you the schematic with like more illustration. So this is a great program, Fritzing. I just try to find something, and this works amazing because it has the Raspberry Pi already modeled and whatnot, and allows you to make specific connections. So if we take a look at the actual connections that I'm making, you can see here, this pin at the top, these two pins are VCC, so they output 5 volts. So what I'm doing is I'm connecting them to that 5 volt lane on the breadboard, and here the same thing with ground, which is located 2 ports down from the top, or 3 ports, sorry, and that's connected to the negative terminal. And then if we look at this other connection that I have here, you can see that this blue wire is connected to GPIO 23, which is a digital output pin. Well, a pin we'll be using for digital output, but it doesn't do any analog kind of stuff. So that's what we're going to be using to control the LED, just on and off. And again, we need that resistor in there to limit the current going to the LED. Otherwise, the LED would burn up and not work anymore. So we're going to wire it, connect it to the resistor in series. We're going to make sure all of this is in series. So the signal is going to the resistor, which goes into the LED, which again, they're on different rows, so they're not connected to each other. And then you're going to connect it to ground to make sure that there's a voltage difference. Yeah. So I know you guys can't ask questions, but I think you got the general gist of what this schematic does. And now we're just going to wire it on this breadboard over here. So let me just stop screen sharing. So I think it'll prioritize my camera feed, hopefully. Ignore it right now, the H bridge, it's on here just because this is the best way to store it for the time being. So what I'm gonna do is connect, so on the Raspberry Pi, I'm gonna connect, again, using the pinout reference from earlier in the presentation. You can also look it up online. I recommend the site pinout period XYZ. It shows you an interactive way of like visualizing all the pins, because we don't have anything, there's no physical indication on the board what pin does what. On Arduinos, it's a little clear because there are not as many pins, and they're better separated. So it'll show you which ones are digital, which ones are analog, and what numbers refer to what pins. But that doesn't happen on the Raspberry Pi. But I know which pins do what for the most part, based on what I prepared for this workshop. So this one in the corner here is going to be my 5 volts. So I'm going to connect that to the 5-volt lane. And then this negative one, which is the 3rd one from that corner, is going to go into the negative terminal. So what I'm going to do next is connect my signal wire. So that's going to be GPIO 23 or physical pin 18. So that should be 4, 5, 6, 7, 8. That should be that pin. Let me just quickly check my own wiring. Yep, that looks right. And I could put it on any row over here for now. Then I'm gonna, so let me just, I guess, bring this up so that you guys can probably see it better. Yeah, so you don't want to put the signal on the terminals here because that would kind of defeat the point, and wouldn't really allow you to control it. So here we have the resistor. I'm going to just simply bend it just so that it can fit on the board. There is no specific direction for current flow in the resistor, so it can go in either direction. So yeah, so I'm going to plug it in on that signal on the same row as the signal wire, and another row that happened to fit the shape that I bent the resistor into. So if you guys look there, you can see that one of the terminals on the resistor is connected to the signal, and the other one's just connected to an empty row for now. Then taking the LED, I'm going to plug in the positive, the longer, I guess, terminal of the LED into the row of the other end of the resistor. And I'm going to make sure to put the negative terminal into ground to complete that circuit. So something like this. So if we kind of trace the flow of current in this circuit, it's coming in from this red wire and it's being supplied to this entire lane. For right now, the lane is powered, but it's not doing anything because again, we want to control based on the digital logic that we're sending to that pin. So for now, the red is not being used, but let's say the signal is coming instead from this yellow wire. So current's going to flow through here into the resistor, through the resistor, and then into the LED, and then back into the negative terminal. So we make sure that this is a closed circuit and that there is current flow. Yeah, so now that we have that done, we're going to move on to the coding aspect of this to actually implement the control of that pin. So let me share my screen again. Which screen do I want to share? Visual Studio Code, that looks good. Yes, let's do that. So, yeah, I'm actually not going to demo any SSH into the Pi. I'm going to run the scripts, but I'm not going to really show you guys how to really do that. If you guys want, again, I'll send some how-to guides to do it later. But I just want to really get to the demonstration of each of these scripts and not really focusing on everything else that you have to do. Well, I guess I'll show you guys what I do to run it and whatnot. But most of my focus is going to be on the logic of the script. So here I have a script. Let me just make it bigger. Yep. So that should be big enough. So let's go through what we're looking at here. So I'm using VS Code to edit this. You can do it a bunch of different ways. I just like using VS Code, and I have like Python installed on my computer. and a bunch of extensions to, change the colors of each of the things. Why is this? So starting off with the top, what we want to do is import the library to control the actual pins. So again, with Raspberry Pis, they've been out for a while now. People have made libraries to help us implement the control for the pins as simply as possible. So doing it, coding it, hard coding it basically from scratch would be very cumbersome, but we can avoid all of that by just using this convenient package that comes with Raspberry Pis. And again, based on the workshop that Audit did, you should know how to import a library. So we're going to do import the GPIO, RPI, GPIO. You want to make sure you spell this exactly as it is with the same case. Otherwise, you won't be importing the same the package. So you're going to do capital R, capital P, and then lowercase I, dot GPIO, all caps. And then as GPIO, you don't have to you can change this GPIO. What you want to make sure of though is that whenever you reference this, it's the same case. So for now, I'm just going to set it to all caps, and in my code, like you'll see that all of just got highlighted. It's all the same case. Now, another important library that we want to use is the the sleep, and that's within the time library. So we're just going to do from time import sleep. So it doesn't import the entire time library, just imports that one function sleep. And this will be used to control, not for PWM, but for changing the signal that we want. Like, let's say we're doing on and off, we'll kind of use that to simulate PWM, but we can't set any specific frequencies and whatnot for that without doing a lot of extra work. So then we have, with this set mode function, what it does is configure the logic of the program to use different references for each of the pins. So in the case of the Raspberry Pi, we have two different kinds of configurations. We have the BCM and the board. So BCM is just the default lane, like coming from the controller on the Raspberry Pi. The BCM is whatever lane it's connected to. So it's not dependent on the board itself. It's dependent on that chip that they're using. So on a different device, if they had the same chip, it'd be the same pin. But you also can do board, which will reference the actual physical labeling, the labeling on the whichever pin it is on the Raspberry Pi. So let me just kind of switch screens to kind of show you guys really quickly the difference. So again, going to that website that I mentioned earlier, pin.xyz. So when we're referring to the BCM pins, we're referring to, let's say here it says GPIO 14, GPIO 15. So the number is what you're going to use to reference that pin. Whereas the board would be referencing, if you can see this here, there's another number, which is the actual proper numbering of each of the pins. I don't want to use that because what you could accidentally do is try to control one of the pins that you shouldn't be able to control. Like, let's say you're going to do pin 2. We don't want to do that in our code because you're not controlling the 5-volt out. That's always going to be 5 volts. Now there is logic implemented in the library itself for you to prevent that, but I want to keep things simple for the most part and just use these bigger numbers that are referenced after the GPIO pin. So switch back to my code. So yeah, so we're going to use GPIO board. That was probably a longer explanation than it was necessary, but whatever. And now we're going to define which pin that we're using. So again, we want to make sure that for this first demonstration, we're just going to use a digital pin just to output 1 or 0. So we're gonna set that to, again, the pin based on that website that we just saw. We're gonna use pin 23. So we're just gonna set a variable LED to that pin number. Now, what we have to do is actually declare what kind of logic what kind of function that pin is serving. So it could be either an input or an output. Right now, we're just outputting a number. So what we want to do is do GPIO setup. We're going to reference that pin number. So when we put LED here, it's actually referencing 23. And then we're going to define what we want to use it as. So we're doing output. So we want to do GPIO.out. We can also do GPIO in, and that would use as an input pin. But that's for a different time. And this next line 13, just basically sets the output logic on that pin. So now that we have that pin set to output, what we can do is output an actual signal. So GPIO output, again, referencing the LED pin, and then the logic that you want to do. So right now we're send it to low. So we're going to do GPIO low. And that will turn off the pin or send 0 volts, which wouldn't be, is nothing, so you can't power anything. Now, the logic of the program is these 4 lines here. Everything before that was set up, and the try and accept and finally loop is something that I would recommend you guys implement in your own code. Simply because when we are using Raspberry Pis, once we configure specific pins in our program, if we do not clear those pins with this GPIO.cleanup, what happens is even though the program ends, those pins are still going to be configured to, let's say, an output pin, and they're still going to be outputting whatever the last logic level was. Now, the issue is when we rerun the script, what we're going to see is that the terminal is going to give us an error. Well, not an error. It's going to give us a warning that that pin has already been used or whatnot. And it might mess with whatever circuitry that you have plugged in. Again, you don't want to short anything. So what we want to do is, this is the most convenient solution that I found, is kind of wrap everything in a try except loop. So this is usually to handle errors. In this case, the error is quitting the program. So you can quit any program in the terminal by doing Control-C. In Python, you can catch that as a keyboard interrupt error. And then you can, in this case, we're just going to print finished. But we want to make sure that we have this finally statement, so that regardless of whatever happens, like let's say if the program keeps running and then just stops on its own, or we interrupt it, regardless of what happens, this statement will always run GPIO cleanup. And that, again, is resetting the pins so that they're not configured when you're trying to run the script again. So again, I would recommend writing all your program logic in the try loop. When you quit the program, you can have it really print anything. And then in the finally, just make sure to include GPIO cleanup. But let's go into the actual logic of this program. So this can either be your favorite thing or a nightmare. This is not good coding practice. So you have this infinite while loop. So this loop will never end, meaning that this program will never stop until we actually stop it by using, again, the Control-C keyboard combination in the terminal. But yeah, so this will always run regardless of whatever changes until we forcibly actually quit the program. Now we're just doing that for demonstration purposes. In your code, you might have it do that until maybe your phone disconnects or something, where it should stop the code or whatnot. But again, for the demonstration purposes, we're just gonna make this infinite while loop. just so that this runs until we ask it to not run or we stop the program. So what we want to do in this first demo is just turn on and off the LED. So we can do that by using GPIO output, again, referencing the pin number, and then referencing the logic that we want to output. So what this does here is it basically turns that pin on or sends a high signal. So the LED is going to turn on. Now, we put this sleep function here, which takes in the number of seconds. It also takes in fractions if you want to do milliseconds. But this will sleep for a second. So the actual program will stop running for 1 second. So let's say normally this runs very quickly. Well, Python's slower than most other languages, but that's beyond the point. Most of this will run pretty much instantaneously. But if we put this sleep function, then it will stop the program from executing for that time, and then it will continue. So this will turn on the LED, keep it on for a second, and then it'll turn it off by doing GPIO low. And then we have another sleep function down here, because what would happen is, let's say we didn't have it. In the execution of this loop, it'll turn on the LED, keep it on for a second, turn it off, but then it will jump back up here instantaneously and turn it back on again. So what it looks like is the LED stays on because it turned on and off so quickly that you cannot see it. So we want to make sure we have the sleep function to make sure that it's off for a second, and then we turn it back on. So let's now run this. I don't know what edits I made. I should be connected to shit. All righty, we are back. Sorry for the delay. We had some technical difficulties again. But now the Raspberry Pi is definitely connected to the internet, and I definitely can SSH into it. So that is good. That is very good. All right. I guess I'm going to show you guys, if you didn't know already, how to do that. So you have to make sure both the Raspberry Pi and your computer are on the same network. And then either through PuTTY or whatnot, you do like, well, not in PuTTY, but you do something along the lines of SSH. This is in Bash, or like this is common in Linux and Mac OS. It's different in Windows. Actually, no, I think Windows is also pretty similar. But I'm going to do SSH. I'm going to put the username, which in my case is Pi, and the host name, so Raspberry Pi. Hit enter. Then it's going to ask me for a password. Sometimes it'll ask you if you want to add the like authentication certificate or whatnot. You just type in yes. But for now, I already did that before, so I'm just going to type in the password. And it'll do a bunch of this stuff and then give me that new kind of I guess like directory, whatnot. So now I'm on the Raspberry Pi. I can run a bunch of Linux commands and whatnot. So I'm gonna just make a new directory for the workshop. So I'm gonna do GPIO workshop. I can't spell. And then I'm just gonna cd into it. CSMer. Also pretty interesting thing. If you just start typing out something and you hit tab, it'll autocomplete with something that you don't want, with something that you want, not that you don't want. And when it has like multiple different versions of the same name, it'll ask you to choose which one. So I'm in my directory. I'm just gonna touch a few files. id.py, id, pwm.py. What else? Servo.py and motor.py. So that's going to make all the Python files in my directory. So if I do ls, you can see all of those files are there. Yeah. So this LED.py that I have open here is on my local computer. It's not on the Raspberry Pi. I'm going to use this Remote Explorer extension to kind of connect to the Raspberry Pi and have all the file system sync. Again, this is one of the possible ways to connect to the Raspberry Pi. You don't have to do this, and it will most likely not work for the Pi Zeros. This is for anything above, I think, the Pi 2, so anything Pi 3 and above should work with this. I also have this other extension here that does something similar, which will work for all the Pi. Actually, let me use this one instead. So I'm gonna make a new configuration. I'm gonna name it GPIO, whatnot. Let me close up this. So yeah, save. Then I'm gonna set the hosting to Raspberry Pi. With the username being Pi. Then I'm gonna pause my sharing so that you guys don't see this. How do I pause my sharing? Pause sharing. I'm gonna set the password to password. Okay, blah, blah, blah. Now, let me just resume sharing. So I've updated the password. I'm gonna hit save and have this configuration. Then when I do connect, was a disconnect, sorry. Connect, it will connect to the Raspberry Pi. There we go. So it loads up all the file system of the Raspberry Pi. I should have specified which. Let me just change that really quickly. Waste y'all's time. So I'm just let me change the configuration. Ignore all this stuff. Passphrase. Yeah, whoa. We're gonna do home Pi. That should be good. Save. Whatnot. I'm gonna disconnect from this guy and reconnect. So now, yeah, now we're in the right stuff. Doing everything good. Everything's fine and dandy. All right. Yeah. So so you can see this is the directory that I created, and then we have these Python files. So what I'm gonna do is just copy what I had over here into this file. Save it. Do terminal. Actually, let me make a terminal session. Yep. Cool. That's how easy it is with this extension. Again, you guys don't have to use it. This is the way I use it because it's freaking fast and simple to use. But if you guys don't want to do it, you can do whatever way you guys prefer. Actually, let me set this to BCM. Set it to BCM here too. Ah, shit. Okay. So yeah, so let me just check, and I'm gonna see the GPIO. Isn't this? Okay, and then, so now that we have the Python file written and everything's good to go, I'm just, let me just plug in this pin over here. All right, so I'm going to actually run the Python file. We can do that by doing Python LED up. Why don't you just freaking autocomplete, okay? So if you guys take a look, let me stop sharing really quickly and let's focus on my phone. You can see that the LEDs turning on and off at a 1 second rate. might be different since this is being recorded on Zoom and whatnot. But yeah, general gist is we were able to control the LED, and that's good. So, yeah, but right now the LED is flashing at full power when it is on, so that's not what we want sometimes. So let's actually go into doing the PWM version of this so we can control the brightness of the LED. So let me just share my screen again. So what we're gonna do is, if you guys, I know during the workshop, I kind of had you guys rewrite it. I should have just made you make a new file and have that. But whatever, this works. So I'm going to open up this Python file here. Let me just copy it into one over here, and I'll go through the code. So let me say this too. So again, we're going to go through most of the setup pretty quickly. We're importing that library that we need, the time function, the sleep function from the time library. We're going to set mode to the BCM. In terms of the LED pin, now we are switching things up a little bit. Oh, I forgot to mention that. Where are my terminal scripts? No terminal. No. Okay, yeah. If you can see the LED is still blinking, is because I never actually stopped the program. So why don't you just freaking. Oh, yeah, so this is still running, so I'll just do Control C, and it's gonna put that finished, and the LED turns off. So that's good. Make sure you do that after, especially since this is a while loop. You want to make sure you stop the program, otherwise it will continue running until you turn off power to the Pi. And if you somehow screwed up so bad that you managed to configure it to run when the Pi boots up, I don't know how I did that by accident, but whatever. So yeah, make sure you stop the execution, and then let's continue. So again, we want to use pin 18 this time. So if we, let me just change screens really quickly. Boom, 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 magic. New screen. So again, pin out XYZ, great website. But now we want to use a PWM pin. So actually what we can do here is, let's say we select the pin type that we want to use, it'll highlight the pin. So the closest one to the power and ground ports is GPIO 18. So that's the PWM pin, or post PCM, post code modulation, whatever. It's same thing, just different terminology. Yeah, and you can read here, it's like a digital representation of sampled analog. So you can go more in, you can research more into PWM and how exactly it works. But for now, we're just gonna quickly demo how to use it, and then go on to the harder stuff. So if you could see, it was pin 18. So what we want to do is make sure that we're using pin 18 to control the LED. Then we're going to set it as an output pin again. That remains the same, even though we're using a PWM pin. You still want to set it as an output because it's not taking input data, it's outputting data. Now here's where the difference really starts, other than just the LED pin configuration, is we actually have to start a PWM instance for that pin. So what we do is we have this variable named PWM, and we set it to this function, GPIO PWM, with the parameter being the pin number as the first parameter, and then the frequency that we want that pin to oscillate at. So there's an internal clock built into the Raspberry Pi, and this is setting that pin to a specific frequency using that clock. So we're going to set it to 50 Hertz. That's pretty good for pretty much everything you guys need to do. And it's pretty easy and simple to calculate stuff if you need to. So yeah, we're going to set it to 50 Hertz. And then this next line is just starting it. So it actually starts the oscillation. At 0, meaning there's no power output. So this is again duty cycle 0. So it's always just no power outputting. Yeah, so it's a flat line now, even though it's pulsing, it's 0, so it really isn't pulsing. Again, you want to wrap everything in a try except finally kind of loop. Just making sure that this last function runs whenever you are executing the program and it stops, or when do you want it to forcefully stop. You want to make sure that you have this GPIO cleanup thing, just so that, again, it removes any configurations done to the pins that will last outside of the runtime of the program. But let's go into the main logic. So what we're doing here is we have this for loop with the variable that's being iterated is duty in the range of 0 to 101, incrementing by 10. So duty cycle, maximum value is 100, minimum value is 0. That's the percentage. So either 0%, 100%. And then here, the 10 is just the incrementer. So we start off at 0. The next value in the for loop iteration will be 10, then 20, then 30, then 40, and 50. And then we have the last one being 101 because it's not inclusive of the last value. So if we were to do 100, it wouldn't go to 100. It'd stop at 90. It'd stop at 90 because if we added 10 to 90, we get 100, and that would be not included in that range. So we want to make sure we have 101. So this is just, so this for loop is going to run 10 times. Now that value for the duty cycle, we are going to change the duty cycle every iteration. So how do we do that? With calling the change duty cycle on the PWM object and passing in the new duty cycle that we want. So we're going to start off with the 0 duty cycle, so off, and then it's going to get brighter and brighter every 2 seconds. So yeah, and this is what the sleep function does. It keeps it at the same brightness for 2 seconds and then increments it. So in terms of wiring, all you're doing is just shifting that wire, I think 2 spots earlier to match where that pin is. Because again, you're not using the digital pin, you're using the pulse width modulation pin or PCM pin. Yeah, so let's actually quickly run this. So if I did everything right, it should work flawlessly, but nothing tends to do that. So let's just cross our fingers and hope that it works. So there we go. So I don't know how well you'll be able to see this, but the LED is in fact getting brighter. With the 50 Hertz frequency oscillation, you can kind of see the LED actually like flickering. Now, if you were to do a higher frequency, this would be less visible. But for the purposes of the servo and the motor control, it doesn't really matter. And I don't expect you guys to put LEDs on your internal comp robots because they serve absolutely no purpose other than like being cool. You can probably ask Albert what that feels like because he actually did that for his internal comp robot, as well as a bunch of other stuff. But it didn't help him, especially the LEDs, and maybe the arms too, just not good. So make sure your mech design is also as good as your electrical wiring and coding. Yeah. But enough of that. Let's continue since it's already, what is it, almost 1 a.m. I'm very tired, but I do want to get this out to you guys so that you guys have something to reference, because I know, again, the workshop didn't go as well as I planned it to. So let's continue. Let me switch screens back to the presentation. Where is it? Is it this one? All right, it is this one. All right. So, oh, no. Go back. All right. So that was the basic of controlling the LED with the digital and analog signal. But now when I do something a little more practical to the robot, maybe even the grabbing mechanism that you guys have designed uses a servo to kind of move whatever piece to like close the claw or open the claw. It all depends on whatever design you guys have. But this is pretty important for most of your internal comp projects. And if not, maybe when you're working RCR, you'll be probably doing something similar. Again, this is a fundamental like aspect of robotics. So the stuff that you kind of do here on a smaller scale for your internal comp project will only get much bigger when you're working on RCR, because the components, like instead of this Raspberry Pi, we have an NVIDIA Jetson, which is like a super small computer. Well, super meaning like really good and fast, but it's also not like a actual full size computer. And it's made specifically for like machine learning applications. So yeah, a lot of the stuff, the circuitry that you'll be using gets a lot more complex when you're moving on to bigger projects. The software is going to definitely get a lot more complex, and the mechanical design is going to get a lot more complex. But this will definitely give you the fundamental knowledge that you need to then make that step and do that, and encourage you to make that, will push you to do that research and learn more about the harder aspects of robotics. I myself started off last year with internal comp, not knowing much. And now I'm the electrical team lead designing a robot. So to compete in a different country. So it takes some time, but as long as your drive is there and whatnot, you can definitely pick up a lot of the stuff and apply it to our main competition robot, your own personal robot, whatever you do. It's just going to be on a different level of difficulty. So that was a bit of a, I got besides the point, but let's continue with the demo. So we have controlling a servo. So how a servo works is you can change the angle that the servo is positioned at depending on what kind of pulse that you send it. So let's, in this image here, we have the diagram at a 1 millisecond pulse. So this is running at, I don't know what that, so the duty cycle in this case is 5%, and it's going to be at this position. At the next, what is it? Whatever 1.5 divided by 20 is, 7.5, I think. It's like it's going to change it to this position, and then at 10% it's going to change it to this position. Now, when we're using the servo, we want to make sure we kind of get the upper and lower limit of the duty cycle. So in the case for these micro server 9G, well, 9 gram SG90s, I found through testing that the range is between, I think, 2.5 and 12.5, I guess, duty cycle. So you have a range of really 10. And that will get you the full 180 degrees on the servo. So again, these servo motors, by the way, only rotate 180 degrees. There are some servo motors that are continuous, but for this application, we don't really need continuous motors, servos, because otherwise it really just becomes a motor with just finer control. So yeah, we'll be using 180 degree servo motors, and now I'm gonna, I guess, show you how to wire them up and control them. All right. So in terms of the schematic and wiring, it's going to be a little more straightforward. This is, I think, a little easier because you just plug it. You can plug it straight into the servo. Usually, you'd want to apply a separate power source for the servo, and then just plug in the logic to whatever controller that you're using. But for the cases of this demonstration, and I guess when you guys are actually doing your robot, you can just plug it into VCC and ground that are supplied by the Raspberry Pi. So Let me just stop. Well, let me go through the schematic really quickly. So again, we want to make sure we have power to the servo and we're completing the loop and we connect it to ground. And then we just have one more wire, that's the signal that's sending that influencing the direction of the servo. Again, we're using GPIO pin 18, the same one we use for the LED, because that's the closest pin to the other pins that we're using. And the wiring, again, is very simple. You just have it connected to power, ground, and signal and whatnot. So that's not too bad. Not live coding yet. So let me wire it up for infinite camera. I'm gonna stop sharing so you guys can kind of focus on the video that I have going on. So yeah, so what I'm gonna do is I'm not really gonna plug it into the breadboard. I can do that, but I would need to use more wires, and I don't really feel like doing that. So I'm just gonna remove all the previous circuitry for now. You could, when you do have to control more than just one servo, let's say you're also controlling the H bridge and whatnot, you want to make sure that you connect it to the breadboard. Otherwise, you won't be able to supply power to more than just one device. But again, for the purposes of this demonstration, it doesn't really matter since we're only doing one thing at a time. So I'm just going to plug in ground to the brown cables. So standard practice is to use black as ground, red as VCC or power in. Here brown is also ground, red is still red. And now that I applied power, the servo actually did move a little bit, but not to whatever position that we need. And then we're just gonna apply the signal wire. So it should be connected like this. You should see that they're pretty much the same. The coloring between the wires is not gonna be the same, but as long as you know which wire is connected to where, you should be good. So also, these come with a bunch of different like attachment head things, blades, whatever, because they're teeth on this servo, and then there's like slot for it here, and you can also screw it in. But for right now, I'm just gonna keep it on so I can remove it, since this is part of one of the kits over there. I'm gonna try to set it so that it's like parallel to the body of the servo, but that's very simple wiring. You can do it pretty easily, not too bad. The only thing is, let's say you are controlling multiple devices, be conscious that you only have 4 PWM pins. So if you, let's say you want to do the maximum combination of let's say motors, so you can have a total of 4 servos that you can individually control. You can also have them two of them set to the same. You can connect them together so that they move at the same time, and that'll allow you to combine. So you use less PWM pins. But let's say you have a combination of motors and servos. The maximum you could get is 4 motors, assuming that they're grouped into twos. So let's say you have a side, you have motors on this side and motors on the other side. And let's say you need turning or steering, whatnot. You can control these two to set them to the same speed, because it doesn't make sense to set them at different speeds. So these will stay the same speed, and these can be set to a different speed or different direction, depending on whatever it is what you want to do. So if you do that approach, you can control 4 motors. Again, they're paired in twos, and then have 2 servos. Or you could also just do 4 individually controlled motors, which does make sense. And it is probably just not at all helpful. And you definitely just don't want to have 4 servos, but I'd recommend, my recommendation is 4 motors, 2 servos. That should be plenty to complete the challenge and whatnot. At least physically. Software wise, it's a little different because you'll be doing more than just controlling the robot. There's also that hacking and whatnot. But yeah, so anyways, back to the point. Oops. Let's go into actually coding for this. So let me share my screen again. Okay, so we're done with the LED stuff. So LED stuff can go bye-bye. Let's open up servo.py. I already have it shit. I already have it written. Just so that I don't have to do it in a moment. Yeah. So let's actually like go through this code. So again, most of the setup stuff is very similar for the different devices that you're using. It only really changes when you're using a specific pin, or and obviously at the logic level, whatever the logic of the program is, that's obviously going to be different. So we're just going to start off importing the same two libraries that we did before, configuring the board as we did before, setting the pin number, same as what we had before, setting up the output pin, again, the same as before, PWM, still same thing. So we can pretty much quickly go through that. We're done with that. Finish. So here, let me kind of explain what's going on. So you can set a PWM signal between 2.5 and 12.5. But I wanted to kind of show you guys how to set it to a specific angle in like degrees, to get that full range of motion from the full 180-degree range of motion. So what I have here is, this is the logic that the program's going to run. It's just going to do an infinite while loop. It's going to take an input from the terminal, and then it's gonna call this function depending on the angle. So let's actually start with this before we go into the actual function that I have here. So this is, again, infinite loop. This is gonna get the input that we're gonna type in the terminal and convert it from a string to a float, because we want to be able to set like a specific angle in degrees or whatnot. And that's what the float cast is going to do for us. And now that we have it stored in angle, we're just going to pass it to the set angle function, which is defined up here. So that's going to keep running. This will actually pause every time it'll ask you for an input. So the program will just stop until you enter something, and then the while loop will continue. Obviously, if you quit the program, then it's just going to print finish and then clean up the GPIO pins. But let's now go into the set angle function. So what we're doing is we're defining the function, and we're passing in a parameter called angle. So the angle is going to be, again, I'm going to set it to a value between -90 and 90. So you have, you could also do 0 to 180, but it's up to you. I'm doing it from -90 to 90. So a good practice when doing any kind of coding is to just check to make sure that the value that you're given as a parameter falls within the range that you want it to fall within. So this is just simply checking if the value that I entered is between that -90 to 90 range. If it's not, then it will just print enter an angle between -90 and 90, and it will not execute the rest of the program. If it were to do so, then eventually I'd be passing in an error and it will raise an exception, and then my program will probably crash. So again, good practice is to make sure that your inputs, even if it's sent from something that you know will probably not change or will always be the right input, just always have some kind of error handling. Or I mean, data validation, not error handling. Error handling is a little different. To make sure that the data that you're getting passed is right. But let's say we have an angle of 45 degrees that falls within the parameters. So this if statement evaluates the false, meaning that the else statement runs. So the math that's going to actually convert this to the duty cycle that we need. Again, we're working with a 10 duty cycle range from 2.5 to 12.5. So we have to convert somehow the degrees from -90 to 90 into, I guess, a value between 2.5 and 12.5. So what we're gonna do is we're gonna actually divide that angle by 18. So let's say we gave an angle of 90. If we divide it by 18, we'll get a nice number 5, which I'm using obviously for demonstration purposes. So if we have, again, 90 divided by 18 equals 5, and then we add the 7.5, that's going to be 12.5, which is the upper limit or the max that the servo can rotate in one direction. If we do -90 and we divide it by 18, that's going to be -5, and we add 7.5 to that, it's going to be 2.5 again. So again, this works with the range of values that we want. If we were going to do from 0 to 180, you would modify this to instead start at 2.5 and then just add that angle that you need. So again, up to you what you want to do. Yeah, that again, you have full freedom with that. You don't even have to use angles if you don't want to. I just think it's much easier than having to remember which duty cycle is going to set it at which angle. But now that we have the math done for that, what we can do is actually change the duty cycle on the PWM pin to the duty cycle that we calculated. And what we want to do is make sure we give the servo enough time to physically move to that position. So we're actually going to call the sleep function for 1 second. It doesn't take 1 second to actually reach that position. It could be less. Just maybe sometimes you want to get it as fast as possible, so you'll just set it to whatever. You would just want to make sure that the difference between the current position and whatever the next position is, it has enough time to get there before this next value runs. So what will happen when you change the duty cycle on the servo to a value that's not 0 is, again, that pulse is going to the servo. So this will start vibrating. It won't move, but it'll start vibrating because you're still sending a signal to it. So what we want to do to kind of stop it from vibrating is actually change the duty cycle to 0 so that it stays fixed in that position. So when we set it to 0, nothing moves. But if we set it again to a value between 2.5 and 12.5 duty cycle, then it does move. So it's in order to prevent that vibration movement, we're just going to turn it off completely, and that will stop any kind of like vibration. Not that it's going to be much of an issue in your robot, but it's something that we really don't need. So we want to just kind of account for it by turning off the signal. It also saves a little bit of power, so that's good. We like power saving. Yeah, and that's the gist of the set angle function. So now let's actually run this. Again, I have this stuff already configured pretty easily for me. It might look a little different for you guys, but I'm just going to do Python servo.py. And now let me just make sure to hold up the servo. If I run this, it's going to ask me for an angle. So let's actually set it to 0 for now. And that's the 0 position. So, shit. Actually, let me stop sharing here so that you guys can see better the actual pie moving. So that's the, I guess, 0 position. Now, let's say I set it to 180. Oh, no, not 180. 90. It's going to move it back. Let's do -90. Boom. So that there you have the full range of motion. You can do that 180 degrees. And then I can also specify, let's say I want to do 23 degrees. It'll do that. And it's pretty accurate. So it'll get you the angle that you need. For the case of like a grabbing mechanism, the accuracy doesn't really matter. You're just doing it open and close. But in case, and if there is a practical application to having a specific angle, you can rest assured that this has a specific accuracy with its design specification within the degree of tolerance. So it's very accurate. That's why for the servo stuff, compared to a motor, the servo will give us the right angle that we need, rather than a motor where it's more focused on the actual motion and speed and torque needed to move something, and less about actual control. So this gives us very fine control of the angle, and this motor, for example, will just keep spinning on and on and on. So yeah, so that's the servo. It's very simple, not too difficult. Maybe it might get a little more difficult when you're trying to control multiple devices at once, but this is pretty straightforward. And yeah, so that's the servo. Now let's move on to the motor and the H bridge. So go back to my Zoom meeting, start sharing my screen. Normally I'd ask you if you can see my screen, but no one's here. So yeah. So controlling the DC motor. So like I mentioned before, we have a motor controller, which is this H bridge here, that allows us to simplify the process needed to control this motor at a different speed and the direction of motion. If we go into, let me see. So let me actually go through the specific pins on the board that we're using, the H bridge, and then kind of go into the wiring so that you guys can kind of get a better sense of what each pin is doing and why it's connected. So what the characteristics when you're like reading the schematic for a chip that you should be interested in are, one, what the pins of each of the what each of the pins on the chip do. So for example, here we have, if you actually look at the board that I have here, I don't know how well you can see it, but you can't really see it, but there's an indent here at the top that kind of shows the direction of the board. And that's going to match what you see on the specification. So you'll see that this little indent indicates the direction of the board. Otherwise, you'd be kind of stuck figuring out which side is which. Which direction is which. But yeah, that's done to help you determine the orientation of the board. And yeah, so now that we know the orientation, we can just follow along with this image here regarding what each of the pins does. So we have here 1, 2 enable. So what this is actually doing is enabling the output of the 1 pin and the 2 pin. So if, let's say, this is set to 0, then these pins should not output anything, or at least the logic set to the input of these pins should not be relayed in the output. What you can also do with this enable is actually control the speed of the motors, because whatever the range of voltage that you give to the enable pin will be reflected in the output. So let's say you give this like 2.2 volts, the output is also going to match that. So this is good. You're going to plug in the PWM pin here when you're setting the speed of the motors. Now you have 1A and 1Y. So normally the A, B, or C refer to the inputs, and then the Y is going to be X, Y, Z, I think, is going to be the output. In this case, it's just A and Y. So A is going to be the input, Y is going to be the output. So when you are plugging in these motors, what you want to do is actually these 2 pins, 1A and 2A, control the direction of the motor. So if you look at this block diagram of what the actual circuit logic in the chip is doing, is basically there are like 4 switches and whatnot, and depending on what you set the inputs to, it will determine what the direction of the motor output is. So let's say, for example, I set 1A to high and then 2A to low, then it's flowing again from high to low in one direction. If I set them both to high, then the motor doesn't move because again, you need that potential difference. And since you have sending too high or too low signals, then there's no movement in the actual of the current through the motor. So you want to make sure that whatever you input for one is different from what you input for two. It has to be the opposite. Same thing for on this side with 3 and 4. You want to make sure what you input for one of them is the opposite of the other. And that's going to determine how your motor moves. So for example, I'm going to, let's say again, I set A to high, 1A to high and 2A to low, then there's a direction. If I inverse it, so I said 2A to high and 1A to low, then it's going to go in the opposite direction. So what we want to do is we can configure these two pins to be connected to a digital out. So it's just it's high or low, and that should be able to help us change direction. So yeah, in terms of the other pins, so everything here in the middle from 2 to 7 is pretty much the same on 10 to 15. What this does is allows you to control two separate motors. So anything you input on this side is going to be different from this side. These are two separated like circuits, but pretty much they're just powered by the same chip and power supply. So again, you have your own enable, you have your own input and output. So yeah, again, it's the same. So in terms of the other pins, the heat sink and ground, you want to make sure that these pins are always grounded. That's where any like heat is going to be dissipated. So you want to make sure you wire all of these pins to ground, and that's very simple and doesn't take too much time to do. But make sure to do that, otherwise, one, the chip may overheat, and two, it may not work because you are powering the chip, but you're not actually grounding it, so there's no flow again of current. So this VCC2 actually represents the input of the input supply to the motors. So let's say, for example, in our case before, we were kind of using the Raspberry Pi to power the motors. Now, when we're actually making the robot, we don't want to use the Raspberry Pi to power the motors because one, the voltage is too low to be powerful enough for the motors. These motors can handle, well, this chip can handle up to 36 volts, which is actually like defined here in the specifications by this VCC2, and then the max being 36 volts. And these, I don't know if they can handle 36 volts, but the more voltage you apply, the more power it'll draw and the faster it'll move. So what you're probably going to end up doing is connecting a 9-volt battery or maybe the power bank that we give you to this VCC2, and that's going to power the motors directly without using power from the Pi itself. So yeah, so you can connect the motors to a separate power source than the Pi. You shouldn't control really anything from the Pi. Again, the other stuff I was doing was simply for demonstration purposes. Otherwise, it won't really run as well as you expect, especially the motors. The servo might be fine. The LED is definitely going to be fine. But for anything a little higher, like especially if you need this motor to drive something more powerful, let's say you are going up a ramp or something, the Pi might not output enough power to actually go up that ramp. But if you plugged in a higher, more powerful power source, then it will absolutely be able to do that. Yeah, so yeah, VCC2 is power to the motors specifically. VCC1 is power to the chip itself. So every chip that you have that you use is going to need some power. So if you don't power the chip, then nothing runs. You need to power the chip for it to perform the logic that it needs to do. So you're going to actually connect that, and you can connect that straight to the power from the Pi, since it's just it's a very simple chip. Again, most of the power that you need for the motors is being provided by VCC2 and is separate from VCC1. So make sure you apply. You can just plug this into the same power lane connected to the Pi or breadboard. Just make sure that again, you don't apply too much voltage. Like here, the maximum is 7 volts. So if you apply more than that, then you risk shorting something, and you do not want to do that. So a good guide to determining how much power you can apply to each of the pins is detailed by like one of the images like this. So I took this off the schematic of the L293H bridge. And multiple companies make the same bridge. And they'll always have some kind of specification that shows what the limits of each of their chips is capable of. So this is a good reference. There's obviously a lot more information on the actual data sheet itself regarding specific ranges of operation, temperature, whatnot. But really what the important part is like the minimum and maximum voltage inputs that you can use. And for some of the logic on the board itself, you might need to, it needs to be of a certain threshold to count as like a high or count as a low. And that's again defined by the schematic with like the 1.5 and here the 2.3. Anything above that is considered high. So yeah. So I'm not going to go too much more into the data sheet of the board. You'll get, if you take a class like ESC 280, you'll get a lot more knowledge and hands-on application, and probably be better versed in, reading a data sheet. But again, for the purposes of internal comp, it's not really necessary. It's just here to spark your, I guess, passion and knowledge seeking, whatever. I know, very, very specific terminology. But yeah, let's go into the schematic. So like I kind of referenced before, in the data sheets, you'll be looking at, you'll be looking at which pins are on each board. And this is a good way to see the actual, where the wires are connected. So again, you want to make sure you ground the board. I don't know why this one connection is this dot connection should not be there. But yeah, you ground the board. Right now we're only using one side. The only thing we're doing on the other side is providing the power for the board itself. So here you have the enable. It might be not, it looks like it's in the opposite direction of what it was in the previous slide, or I guess the future slide, but we have the enable, we have the input, we have the output, 0, 0, the output, input, and then the power to the motors. And then on this side, we have it for the other motor that can be connected. But really what's important here is that we ground this side too, which I haven't done in this, but actually I did. Yeah, it just looks weird in this schematic, but in this schematic, you can see that both sides are grounded and now apply power to the board. So let's, I guess, reference the schematic here, or drawing. So you see, I connect to the lanes like I would normally to apply power. What I've done here is I have 2 wires connecting both sides because they are not connected to each other. So this will just make sure that both sides have ground and VCC power going to them, so that if I have to connect something on the other side, I can just wire it up pretty close rather than bringing a wire across the board, which you don't want to do. In any case, you don't want to have wires always going on top of a board, going across the board. If you can simplify the route that the current has to take, it's the best practice, just to make the wiring cleaner and easier to debug visually. So yeah, so we're gonna pass in 3 controls to this board. 2 of them again are for the direction, so we want to make sure they're the opposite of each other, but they have to either output high or low, and the opposite, obviously the opposite is going to do the opposite. And then we have that signal wire to the enable That's really gonna help us control the speed of the motor. Yeah, and then in this case, we're just controlling the power direct to the motor from the Pi. Again, that's not what you're really gonna do for your robot. You're gonna give like a 9 volt or something else to it. Because the power from the Pi is not gonna be enough. So yeah, now that we have the schematic done, let's go with, I guess, driving. Okay, I didn't add these slides. Albert, if you did, thank you. But this code looks a little complicated, so we're just gonna go with the one that I made for the workshop. So let me just switch back to, oh, actually, sorry. Before we do that, let me just actually show you guys how to wire it up. In real life and not on the drawing over there. So I have this handy dandy box full of already like what's it called? Pre-stripped wires and connections, and they're all of like different lengths. So I'm gonna use this to kind of quickly plug everything in. I don't know, you guys might have to strip your own wires and do this whole process manually, which is going to take a little longer, but it's a good thing to start kind of getting used to, because in class and whatnot, if you're an ESE major, you're probably going to be doing the same thing. So I'm just using this because it's more convenient for me at the time. And I don't have to worry too much. So also, don't really worry about the coloring of the wiring. I know you should have black and red, but I do not have a black wire that's that length, so I'm just going to use 2 reds. Just making sure again that I plugged everything in the right way. So we want to start off with the power to the board and the power to the motors. So if you remember, this pin up here was actually the power to the board. So we are going to, what you want to do usually is make sure you plug in as far away from the chip as possible. So you want to kind of go from the outermost lane towards the middle, which means maybe this connection, this piece is a little too big, so I'm going to get a smaller one. Yeah. All right. So I'm going to use one of these smaller connectors and just kind of plug into this first pin here, and boom. So this is giving that 5 volts in to the board so that the board is powered. But it doesn't matter if we don't ground it. So we got to make sure, again, we want to ground each of these pins in the middle. Now, I'm not going to do all of them because it's really not necessary. It is best practice to do so. But for the sake of time and my sanity, I'm not going to do it. Shit. Yeah. But good practice again would be to ground both of these connections for better heat distribution and making sure that nothing's running hot. Okay, so I grounded it on both sides. Now what I want to do is also put in the power for the motors. So I'll mention it again, but we're going to power from the Raspberry Pi for the time being. Normally you wouldn't do that. You would power from an external power supply or power source. Sorry, I can't get this damn thing. All right. All right. So let's plug this in. So that's the enable. That's power into the motors. So we are going to put it here. There we go. Perfect. So that's the first thing you want to do. Just make sure you have power to the motor and power to the board. So I can just verify once I plug in the Raspberry Pi into this board here, It's going to be connected to the positive lane. That's going to go to the motor input. Well, not the motor input, the motor power. And this is going to go into powering the board itself. And then both sides are grounded. So we're good here. Now, the next step comes the connections that we need to make to, let's do the connections to the motor itself. So we want to make sure that the motor is connected to the output pins of the board. So we're going to, let me just reference the schematic really quickly again. Just so I don't want to put it in the wrong pin. So the output pin, okay. So the output pins are going to be the ones toward, so actually, let me just show you guys close up what this looks like. Yeah. Again, there's also a schematic on the presentation. There'll be something after I finish this recording. So I'm gonna plug the ends of the motor to the pins, I guess, right next to the heatsink and ground pins. So it should look something like that. You have two pins in between the two cables, and those are the output pins. Now, let me just disconnect my servo stuff. My outputting angle. Hopefully, oh, I did not exit. You always make sure to stop the execution of your Python program, especially if it's an infinite loop. I always forget to do it, so I'm probably going to break something in the future, and it's probably going to be expensive. And it's because I wasn't being careful. Don't be me, be better. Yeah. So let's move on. So what we're going to do now is just apply power to the board. So I'm going to plug in the VCC and ground to the respective lanes. We're going to have the signal wire again connected to the same pin 18. We're going to plug that into, so we're going to use this side of the board. We're not using the other side for this demo. It does work with two motors. I just don't really want to do it right now because it's not necessary for demonstration. So I'm going to plug in this signal wire. Let me make sure that's, yeah, this signal wire into the enable row for the board. Now what's left to do is just the what's it called, the direction input of each of the pins. So I'm actually missing female to male. So let me just get that really quickly. Also, another thing to mention, these wires that I'm using won't be provided to you in your kits. If you want, you're more than welcome to come to the lab and pick up the wires, whatever you need for your project. Yeah, for my internal comp, we used my friends, my teammates, wires for the most part. You guys are also more than free to get your own wires if you want to. If you don't, you're welcome to use the lab stuff. But we don't have very limited, sets of these wires. This is one of two boxes. The other one's even smaller than this. We might order some more soon, but just be mindful of how many you're taking, because we want to make sure that everyone has a chance to kind of wire everything up to get it working. And then if they have to have any additional features, they can do it, assuming that we have enough for everyone. But yeah, that's beyond the point. Let's go back to, let me just double check the pins that I'm using for this wiring. So we're using pin 18, same as before, pin 24 and pin 23. So I'm just quickly checking to make sure I know the reference location of those pins. So this is pin 23. That is not a good wire. Okay, yeah. There's normally a little friction to the wire when you plug it into the pin, but this wire is not good, so I'm gonna get another one. Or another wire. So, oops, wrong end. I'm gonna plug that into 23. I'll plug that into 24. They're right next to each other, so they can't be too difficult to plug in. And then it really doesn't matter where exactly, which ones you plug the pins into the inputs. Doesn't matter. Like again, it's just setting the direction. So if you get the wrong direction, you can change it via software. It's not that bad. The motor's still gonna run. It's just not gonna be in the right direction, and you can always change that or switch the pins. Again, you can either change the way the motor's plugged in, change the way the signal wires are plugged in, change the way that your code is outputting logic. Bunch of different ways to do the same thing. Doesn't matter for this purpose. Well, for this workshop, but yeah. So let's move on to the code. So the code is not too difficult. We're just working with a little more outputs. So we do have to do a little more configuring of the pins to make sure that we have everything ready to send like a signal to. So I hope you guys can kind of see what the wiring kind of looks like. I'm gonna try to get it as close to the camera as possible. It's not the best. I would recommend just referring to the schematic as it has the same wiring. But other than that, let's go back to the code. Well, let's go to the code so that we can get this thing running. All right. So let's close up the servo stuff. Let me open up the motor stuff. Motor, copy, and paste. All right, and close this up real quick. So let me say this. Go away, go away. So I didn't make comments. I made comments on the other ones, I think. So I will make sure to comment this just to help you guys with like figuring out what it does, because it could get a little like confusing to know what something does after a little bit of not interacting with it. But again, these are the same 3 lines from the other 2 files. Well, 3 files. Now we have more pins that we have to configure. So you want to make sure you have the input for. So this is assuming you have 1 motor, depending how many motors you have. So let's say if you're running another motor on the same side as this one, then you would need 5 different oh no. No, you'd only need these 3 because they would be moving in the same direction at the same speed. So you'd only need 3. But let's say you use both sides of the chip, then you would need 6 because you need to do the enable for the other side and then both inputs for the other side. Now we're only doing 1, so we don't need all the 6. So you need 3 here. So you're going to do the input 1, the other input, and then the enable. Again, 23 digital, 24 digital, 18 PWM. And you also want to make sure you set up all those pins as outputs. Then you're going to also want to set up the PWM. So you do the PWM with the M1 enable pin and the frequency, which is 50 again. And then you're just going to start the oscillation of the pulse. So again, I have another function here, but let me focus on the actual like loop here. So again, we have the try except file A, just make sure, clean up and whatnot. We have another infinite for loop, and we're taking in a value for the speed of the motor. And then it's going to pass that into move motor at speed. So let's go into this function that I've created. So what I've done is I have combined both the speed and the direction. So this is kind of like, what's it called? What has a direction and not the language? whatever. I was trying to make a connection to physics, but whatever. So this has a speed and direction to the movement of the motor. So the range is going to be between negative 100 and 100. And this whole line, the speed, since it's 0 to negative 100 to 100 and whatnot, it's going to match the duty cycle. So it's between 0 to 100. And the only thing we're going to change is if it's positive or negative. So what I'm doing here is if I get an invalid value for the speed, I'm just going to print that out and then I make sure that the motor is off. So I do this, I added these in case, let's say I'm already running the motor and then I input an invalid speed. What it does is not only will it not continue running the motor at the same speed, it will just turn everything off. So let's say you had it at 50% speed or at 50 speed, and then you put it at negative 300. What it's going to do is it's not going to keep running at 50. It's just going to stop. And that's what that does. And then this return statement just stops the function from continuing further on. But it only executes if this first condition was true. So assuming the speed is between negative 100 and 100, then I'm just going to check what the direction is. So if I put 100, then that's the positive direction. And this evaluates the false, and this will go to the else statement. Let's say the speed is negative. Then what I'm going to do is I'm just going to output the specific direction that I want. So I'm going to put low on one pin, high on the other, and that's one speed. And then I'm going to set the duty cycle to the negative of the speed. So since the speed is less than 0, speed is going to be a negative value. And we want to make sure it's positive for the duty cycle. So it'll just convert this to a positive value, which works with the duty cycle. And then again, whatever the speed is going to be the duty cycle for that. But let's say this speed is now positive. So this value is the false and this is true. Then I'm going to inverse the direction. So here I had M1 input 1 to low. Now I have the M1 input 1 to high. So this is a different direction. And again, same thing with 2, it's going to be the opposite. And then here I'm just passing in speed because again, it's a positive value. Duty cycle is positive. We're all good. So yeah, that's basically the very basic gist of it. That's literally all you need to control this thing. And let me, I guess, show you it running. So we have everything connected. I'm gonna run my handy dandy terminal thing magic. Bada boom, bada bye. All right. Let's do Python. Motor.py. Now, if I run this, it's going to ask me for a speed. If I set it to 0, nothing happens because no speed. Let's set it to 100. I want to see if there's a good way I can show which direction it's moving in. I don't think the servo thing is going to quite fit. So maybe this piece of tape will help me out for the time being. So yeah, let me set it to 100. And it's not working. So let me just debug my circuit really quickly. Power's going in. That's grounded, that's powered. I have found the issue. I don't know why I connected the signal wire to the ground. Don't do that. Be better. Wait, stop for a second. Thank you. So yeah, always double check your wiring. Don't do what I did and assume that my wiring is right. Always double check it before you even apply power to the board. Because if you did wire it incorrectly, you again have the risk of shorting something and you don't want to do that. So I would recommend doing all the wiring before you plug in the power. So I know I did the power first. Don't do that. Just wait. Check your wiring. If you're not sure if it's right, then ask me or someone else. When you ask me, I will know if it's right or not, and I won't do something stupid like I just did. Yeah. So now you can see that. Let me set it to a slower speed. You can pretty much tell, let me also stop sharing. So I focus on the camera. Yeah, you can tell what direction it's moving in. That's pretty clear. Let me now give it the opposite direction. So let's do -20. So now it's gonna turn in the other direction. Crazy, right? This is absolutely insane, mind blowing. Again, it's very simple. That's what this chip is. That's why this chip is so convenient, because otherwise you would have to do a lot more to achieve the same thing. And again, I can still change the speed. Now it's faster. Let's go even faster in the opposite direction. Perfect. Now set it to 0. Boom. Magic. Voila. Yeah, it's pretty straightforward. I just want to make sure you guys know all this stuff, because I know I wasn't able to cover it in the workshop, and this is probably one of the more important aspects, the actual movement of the robot. So pretty simple. If you need to like review this part multiple times, I'm gonna try to see if I can like upload it to YouTube and have the different timestamps on it. If it's there when I upload this video, then I did a good job. If it's not there, then you can pay me all you like. I don't really care. But yeah, that's been the coding. That pretty much summarizes everything that you guys need to know for the GPIO Python workshop. Again, I'm sorry for the people that came in person that weren't able to practice, because some people were able to practice on the Raspberry Pi, some people weren't because of connectivity issues. I'm sorry I wasn't able to cover all the material during the appropriate time. There was an issue with the Raspberry Pis. I assumed they had already been flashed and formatted for the Pi, for the workshop, and that they would all work out of the box. But obviously that wasn't the case, and that's my fault. I should have done more testing beforehand. I was just in a rush, and midterms kind of get in the way. But if I do another workshop, I'll make sure definitely plan it out better, and stick to a better time frame than I did. I know this video is also a lot longer than I wanted to be. That's why I kind of want to split it up into sections. So you're probably going to be seeing this tomorrow. Hopefully, I'll have it posted. I'm going to make sure to edit it a little bit, save some time in some places where it's unnecessary, like me flexing for 20 minutes, absolutely unnecessary. Maybe I'll keep it as a bloopers clip, but yeah, that's also, let me make sure to stop my Python script. God damn. So yeah, that is the GPIO workshop. You guys can use this as a reference again. I will be uploading this video. I will be uploading the schematics. I'll be uploading the code. So you have everything that you need, as well as the presentation too. You have everything you need there. I might make some additional material to cover some stuff that maybe is less frequent, like in terms of like you using it, but it might still be important down the line. I just have to make time to do that. But yeah, so this covers basically everything you need to know about GPIO minus analog and digital input. We've done a lot of output stuff. We haven't done input stuff. I wanted to use like a what was it, a potentiometer to kind of control the speed of the motor. But for some reason, it's a lot more difficult to do on a Raspberry Pi than it is an Arduino. So I didn't do it. But I could also host an Arduino workshop. I know IEEE does a lot of Arduino workshops. So you can also go to them and they will show you how to do the analog input. But also, since the internal comp is using your phone as the main controller, there really isn't the need to show you guys that kind of input. But if you are planning to do RCR, then obviously it is important, because you're taking input from a variety of different sensors. And that's definitely important. You want to make sure you know how to do that. So I'm sorry I wasn't able to show it in this workshop. I may make another follow-up workshop, or I don't know, maybe just a quick video kind of going through it, or in-person demonstration, whatever I decide to do. If I see you guys need that kind of lesson and that material kind of taught to you guys. But yeah, it is now almost 2 a.m. on October 19th. Lab is still open. Thank you guys for watching this video. If you haven't gotten to this part and you just skip through it, that's still fine as well. Again, sorry about the in-person workshop. I really planned for that to be a little smoother. Hopefully this video kind of makes up for it. Yeah, that's about it. Yeah, I'm really tired, so see you guys. Goddamn, where's Zoom? So what do I gotta do? I got to pause the recording.